Welcome to this Forge College Explainer. I'm your host, and today we're diving into testing and resilient error handling. We're transitioning from that beautiful, highly secure vault you built in our last monitoring and compliance lesson straight into the testing lab for our capstone comprehensive Ether transaction system. You know, we've poured the digital concrete and we've set up the tripwires. But honestly, as any good developer knows, a vault isn't truly secure until you've strapped on a ski mask and actively tried to break into it yourself. So today, we're getting our hands dirty with applied solidity testing to make absolutely sure our contract stands unshaken against the chaotic reality of the blockchain.
So here is the million-dollar question, and I mean that literally in some Web3 cases. What happens if an attacker tries to withdraw twice before our contract even blinks, right? Now that our blueprints are drawn, we're going to intentionally hire ourselves to break in, smash the windows, and let a few gremlins loose on our smart contract just to see if it holds up. It's one thing to write code that works when users behave perfectly, but it's an entirely different beast to write code that survives when users or malicious scripts do everything in their absolute power to break the rules. We are actively hunting for those tiny microsecond windows where logic can be twisted.
Think of this agenda as our engineering schematic for today's stress test debrief. First up, breaking your smart contract. Second, double withdrawals and reentrancy. Third, gas griefing and events. Fourth, writing the debug report. And finally, hardening the final build. Let's get right into it.
All right, Section 1, breaking your smart contract. Let's identify and reproduce some nasty bugs.
Okay, so we have this pristine baseline, right? Functional guards, audit-friendly logs. It's kind of like building a masterpiece of a bank vault. Polishing up the titanium doors, carefully setting up the lasers, and then just handing a sledgehammer to a team of highly caffeinated engineers and saying, hey, have at it. We must ruthlessly attack our own creation using deterministic hard hat testing. By spinning up a local JSON RPC node, we create this controlled laboratory environment. We simulate deposits, we force unexpected transaction orderings, and we actively try to make the contract's internal accounting drift away from the actual Ether balance. I know it's tough love, but it's really the only way to build true resilience.
Moving right along to Section 2, double withdrawals and reentrancy. Time to sketch out the first major threat vectors.
Think about the gap between expectation and reality for a second. Imagine trying to buy a coffee with your debit card while simultaneously withdrawing your last $20 at an ATM. You're basically hoping to complete both actions before the bank servers can update your balance. Well, that is exactly the double withdrawal race we've got to prevent in our smart contract. If we send the Ether before updating the user's internal balance, a rapid second transaction might just sneak through, creating free money out of thin air. No way we're letting that happen. We need to ensure that second transaction hits a brick wall and reverts with an insufficient balance error.
So the crucial point is understanding how this exact race condition evolves into something far more dangerous, reentrancy. It's essentially the boogeyman of Web3. Reentrancy is an attack where a malicious contract is repeatedly called before its first execution finishes, just draining funds in this devastating loop. To block this notorious attack, we deploy an attacker contract right inside our test suite. We tell this attacker, hey, try and re-enter our victim contract mid-transaction. We want to see if our guards, specifically our non-reentrant modifiers, successfully step in, hold up a stop sign, and force a complete revert of that malicious transaction.
By looking at our blueprints, we can see the absolute crucial fix is strictly updating the internal accounting balance before we ever allow an external transfer of Ether out of the system. I mean, it sounds so incredibly simple, right? Yet ignoring this one rule has cost the blockchain industry hundreds of millions of dollars. You literally must deduct the user's balance in your contract's memory first. Once the ledger reflects a zero balance, then you hand over the cash. If a reentrancy attack tries to loop back around, the contract checks the balance, sees zero, and rightfully rejects the request. Boom, thwarted.
Okay, Section 3, gas griefing and events. Let's see how we handle sneaky partial failures. Let's take a look at a really subtle attack known as gas griefing. This is where an attacker sends a tiny, insufficient gas stipend to intentionally force a failure. Imagine taking a taxi, handing the driver exactly enough money to get 90% of the way there, and just hoping they crash the car when the meter runs out. That's kind of what's happening here. The attacker wants to see if failing halfway leaves your contract in some weird zombie state. We test for this to ensure the contract gracefully reverts rather than corrupting our ledger. We simulate this in our lab so that if a transaction runs out of gas, our contract rolls back the entire state or handles explicit compensation paths.
Now, even if the logic holds up against all these attacks, we still aren't done. We have to run expect event-style assertions to guarantee our audit logs perfectly match the schema we laid out in our integration docs. Think about it. If an alarm goes off in a bank vault, but it doesn't tell the security guards which door was breached, it's pretty useless, right? We need to verify that our events are emitting the exact indexed fields, that the payloads match our promises, and crucially, that they are emitted at the exact right program point, which is almost always after all internal state updates are totally secure.
All right, on to Section 4, writing the debug report. Time to document our victories. This structured testing loop, reproduce, implement, verify, is exactly how we convert integration hypotheses into hardened code and concrete audit evidence. We don't just randomly change lines of code until the red arrows turn green. No way. First, we write a test that reliably and deterministically reproduces the error. Then, we implement the most minimal, surgical fix possible. And finally, we verify the resolution by rerunning that exact same test, proving definitively that our specific fix cured the specific disease.
Let's categorize our assaults with a test matrix. For the double withdrawal case, we fire off 2 concurrent withdrawals and demand that the second one reverts. For reentrancy, we command our attacker contract to strike, expecting the attack to be completely prevented without duplicating balance deductions. Mapping this out is literally the cornerstone of trust for anyone interacting with our system in the future. It demonstrates exactly what actions we take and the precise, safe behaviors we absolutely expect our contract to exhibit under pressure.
This report artifact is super crucial because it communicates to future auditors not just what broke, but exactly how you validated the fix against the original acceptance criteria. You are basically handing them a master key to your thought process. By including the issue ID, the exact reproduction commands like a specific hard-hat test command, and the precise commit hash of your fix, you eliminate all guesswork. And hey, don't be afraid to document remaining residual risk. Acknowledging that a certain edge case might still require fuzzing or deeper stress testing shows incredible maturity as a developer.
Finally, Section 5, hardening the final build. Let's wrap up and establish the laws. Keeping these rules centralized ensures our Capstone repository inherits demonstrable resilience against any gremlins we might encounter on mainnet. These are your non-negotiables. First, always use explicit non-reentrant guards on sensitive functions. Second, perform all internal accounting before you even think about making an external transfer. And third, treat your audit logs and events as first-class outputs, testing their fidelity just as rigorously as you test your financial math. If you stick to these principles, you aren't just writing code, you are engineering trust.
I cannot emphasize this golden rule enough. Continuously applying the checks, effects, interactions pattern is what transforms a fragile script into an impenetrable production-ready vault. You check the conditions, you apply the effects to your internal state, and only then do you interact with the outside world. It is your ultimate shield. Memorize it, print it out, and tape it to your monitor. It is, for sure, the single most important design pattern in smart contract security.
So, your blueprints are stress-tested, your guards are proven, and your debug report is pristine. You've successfully navigated the darkest corners of smart contract vulnerabilities and come out the other side with a hardened, unshakable system. Thank you for joining this Forge College Explainer. Be sure to merge your debug report before our next lesson on the complete Capstone build, where we're going to bring all these pieces together. And please, visit forge.college to learn more about this subject, dive into deeper Web3 topics, and continue your journey toward mastery. Until next time, your blueprints are stress-tested and audit-ready, but are you prepared to assemble the final Capstone build? Keep testing, and I'll see you in the next explainer.